Alright, so hello and welcome back to the second video about understanding NMR. And if any of the ideas that are discussed in this video that rely on the last video are not solid in your mind, I would defer you to watching the last video that was made about the NMR, the first one with the introductory ideas that I'm going to rely on to introduce the next ideas. First of all, we're going to talk about the relationship between the magnetic field, and by magnetic field I mean the homogeneous magnetic field, on the energy of the spin levels or spin states or spin orientation. And this is just a review from the last presentation. We're going to review adding up the spin states, the respective vectors, and the spin lattice versus spin-spin. What do those mean? We're going to discuss the 90-degree pulse, also referred to as the radio frequency pulse, and what the resonance is. And if everything that I just said makes no sense to you, although you watched the last video, just don't worry about it. We're going to make our way in baby steps explaining those different terms, I promise. So let's get started. The relationship between the magnetic field and the energy spin levels. First of all, let's redefine the magnetic field. The magnetic field, by that I mean, let's just say I have a cylinder and it has a bunch of nuclei that are spinning in random directions. I can apply a homogeneous magnetic field, which is a magnetic field that is uniform throughout, and cause a specific orientation either with or against. So far you should be with me, and hopefully you are. And what I mean by that is that we already learned in the last video that we have a distribution of nuclei that spin with the magnetic field. This is the magnetic field direction, and a few that spin against or orient against or anti-parallel or unfavorable to the magnetic field. And there's an energy difference between them, being that those are in the ground state, so to speak. These guys in the upper level oriented against or unfavorable to the magnetic field or anti-parallel to the magnetic field, all these guys are actually in effect have more energy than these the ground state. It just so happens is that if I increase the energy of the magnetic field, and this is, by the way, measured in units of Tesla, but if I increase the energy of the magnetic field, the distance between them, the energy between these two levels is going to be greater. And that's what I mean by that. There we go. And that's what I mean by that. And it's present in the presentation in the form of this graph, and this graph should be pretty easy to understand. This is the energy, which is the energy difference between these two levels of the parallel and anti-parallel spin states. And this is the magnetic field strength. That means that I'm starting from zero magnetic field. I haven't even applied the magnetic field. This is my tube. I haven't even applied the magnetic field. So there isn't really an energy difference because no one is aligned by any force. So we're here, there's no real energy difference in the sense that there isn't a gap between two spin states. But the further I go towards the y-axis, the more I'm going to have energy difference between these two spin states. And if I have a greater, let's just say this is 1 Tesla. This is 1 Tesla, and this would be 3 Tesla. So now the energy difference between the two spin states is going to be greater. This is greater. This is more energy. And if I apply 5 Tesla, you can already imagine I added another one more. This I'd have 4. The energy difference is considerably bigger. And what we should prepare for, this is an understanding. This is a principal understanding idea for a question along the lines of the energy of the magnetic or the energy between the two spin states is linearly proportional to the strength of the magnetic field applied. True. Let me repeat that. The energy between the two spin states is linearly proportional. That means that when one goes up, the other goes up. So the energy between the two spin states is linearly proportional to the strength of the magnetic field applied. And that is true because when I apply more, the magnetic field goes up, the strength of the magnetic field goes up, the difference in the energy levels goes up. And that's what I really mean. And when I talk about magnetic field, I obviously am talking about the homogeneous magnetic field, not the very tiny, minute magnetic fields that these nuclei have, that they possess. So this is the relationship between the homogeneous external magnetic field. This is also referred to as external. I'm going to put it here. And if you're going through lecture slides or notes from the internet or ebooks or even the Medicina book, there are so many terms to describe the same thing. Whereas you can be wondering, what is anti-parallel? Oh, it's actually aligned against. And what is a spin state? Is it the same as a spin orientation or as a spin level? So I'm trying to incorporate all the terminology. So external magnetic field is the same as saying the big homogeneous magnetic field that I'm applying to my sample. Perfect. So let's keep going, and we're slowly doing the baby step thing. And this whole thing should be, at least to an extent, familiar to you because this is from the last presentation. This basically means that when I'm applying a homogeneous magnetic field in this sample, I'm going to have some align with my magnetic field, like these guys, and some aligned against. It's not necessarily going to be the ratio of 5 to 1, but this is just our ideas. Now, if we add up all these vectors, this is what we would get. We would get different vectors that are generally aligned with this vector. And if we add them all up, we would get this vector. And this vector is commonly referred to either, and I'm going to write down all the different terminologies, could be referred to as the longitudinal vector, V for vector, or the spin lattice vector, or it's commonly referred to also as T1, whereas T1 refers to the time in which the time that is associated with the relaxation of this vector. But whenever you see T1, they really mean this main vector that arises from adding up all these smaller vectors. And this would be a good time to introduce what do I mean by these smaller vectors. All these small vectors are basically all the respective vectors for those different nuclei. And this also has a name. Each of these small vectors is either referred to as the transverse. And we'll see why it's referred to as transverse, because it can actually drop when we apply energy to it. It can actually drop. So when it drops, it's called transverse, or spin vector, V for vector, or T2. So far, so good. And we can actually keep on going and get to the essentials of NMR. And if you understand everything up till this point, then there is no reason why you can't understand what's going on easily. So you already know what this is. This is just the depiction we had before. The green vector here is you can say the spin lattice. This is a spin lattice. This is the green vector here. And all the orange vectors are all the little magnetic fields associated with the nuclei that are aligned with the homogeneous magnetic field direction. And now we're going to talk about the 90-degree pulse. Now, what we really need to know before we talk about what the 90-degree pulse is, and by the way, the RF pulse or radio frequency pulse and the 90-degree pulse are essentially the same thing. And I'm going to explain exactly why, but it's really important to me that I would mention all the terminology. So if you hear someone discuss this one, or you hear someone discuss this one, you will be the one that knows to make that distinction that they're both the same. So what is essentially going on? What I really am using NMR for is I'm taking all these different nuclei and I'm gaining information about their environment from their individual spins. Well, we already said these spins are random no magnetic field is applied. And these spins are affected by the type of nucleus, the quality of nucleus. I'm also going to write it down. I'm going to write it down. I'm going to write it down here. What affects the spin of the nucleus? First of all, the type of nucleus. This is before we even introduced a homogeneous magnetic field to it. So the type of nucleus, and obviously the chemical environment, and the strength of the magnetic field would also strength of magnetic field, and by magnetic field I mean the homogeneous magnetic field that we're applying. All of these affect the way this little guy will spin. Now imagine if I know these two variables, because I know what type of nucleus I'm solving for, I know the strength of the magnetic field I'm applying, I can get information about the chemical environment, which is really what I want. Because if I can map what's all around these hydrogen nuclei, I can pretty much map what is in my sample. And that's the information I want to get. Perfect. We're slowly making our way. And the way for that to happen is, if you can imagine, let me just make some room here. Make some room here. If you can imagine, what we really need to do is to somehow find a way. Now that we've aligned everybody up, we've aligned everybody, all the different nuclei, and everybody's lined up. If we only had a way to get these little spin states, or the individual spin states, for a second to spin according to their chemical environment. So in order for that to happen, for them to spin according to the chemical environment, because let's just say there's this guy, if this guy is in a given chemical environment, it would like to spin this way. Instead of spinning with the magnetic field, it would like to spin in that specific way. This would be its spin. And I can interpret this spin and figure out that it has specific chemical environments around him. What I need is to give some energy, find a way to give some energy to this guy to be able to escape this big magnetic field. And how do I do that? Well, let's consider what we already said. There's a radio frequency thing here. So what do we mean? Radio frequency is essentially electromagnetic radiation of very long wavelength, very short frequency. So we can say very low energy. Very low energy. Obviously, non-ionizing energy. And this is often a question that comes up in exams about NMR and MRI, whether or not they use ionizing radiation. So they do not. They use radio frequency. And radio frequencies are electromagnetic pulse, which means that they have a magnetic component associated with them. That means that if somehow I can find a way to give that fire an electromagnetic radio frequency pulse, and we're using radio frequency because its energy is associated, is right around the range of the energy between the two spin states. Remember, we were talking about the energy between the two spin states? This energy pretty much correlates to the energy of this radio frequency. We can obviously, being that we know what strength of magnetic field we're using, we can solve for exactly what frequency we need. But basically, if I find a way to shoot a photon at these guys, or rather at this guy right here, the energy, or rather the magnetic component from the radio frequency, will be able to interfere with the individual magnetic component of our spin or individual spins here. So how does that happen? Let's just say I'm taking just one of these guys, one of these individual spins that is pointing in this direction. Obviously, if I add up all of his friends, I'm going to get the big lattice vector. Start using these. Oh, there's an E missing here. Using these terms. So I'm going to take one of these guys that is spinning according to this is its spin, or you can think about this individual spin as its resonance. Okay, and we're slowly making our way. So I'm taking this little guy that is spinning according to the, and I'm going to put this here according to the homogeneous magnetic field. And what I'm doing now, I'm going to take the radio frequency that corresponds to the energy level it is in, that corresponds to the strength of the magnetic field, and I excite it. And I'm using a pulse. Why am I using a pulse? Because what I really want to do is I want to get this guy to go from being with the orientation to the magnetic field to going back to the way it used to spin on its own, so to speak, with respect to its environment. So I just want a quick pulse because then I can measure what's going on here and then it's going to go back to its original state. And if this is not very clear to you, we're going to go through the entire process and baby steps starting now. I fire the radio frequency. Its magnetic component is going to interact with this magnetic component of the individual spin. Now what's going to happen? What's going to happen now is that this guy is going to experience a drop. Instead of orbiting around like this, I'm going to switch colors, but it is the same. It's the same nucleus. It's going to drop down, and it's going to spin according to its environment, according to its chemical environment, and this will be its resonance. Its resonance will be very visible because it dropped down. So instead of having a resonance, we can just draw a cone. So let me do this. Instead of having a resonance that is the resonance of this homogeneous magnetic field, it would have a very wide resonance that we can detect. And how can we detect that resonance? Well, we said that this little guy dropped, and now you can think of it as spinning this way now. Spinning this way now. It's going to keep spinning. And what's going to happen is it's going to slowly, being that I emitted a pulse for a short amount of time, I only excited it for a short amount of time. So it's slowly going to go back to this situation. So as you can imagine, let's draw it here. I have my little guy here, and it's rotating around this big homogeneous magnetic field orientation. I fired the pulse at it, and it dropped. And now it's oriented in its own frequency. And slowly it's gonna recover, because the homogeneous magnetic field is always present, and this was just a pulse, so it only got the energy for a short amount of time, and then it relaxed and went back to this orientation. And as it is doing that, it emits energy, and I can read this energy. So let's go back and do this one last time. So what happens? I have one of these spins. These are individual spins of the nuclei that is aligned by the homogeneous magnetic field. Very good. I'm firing it with a radio frequency electromagnetic pulse with magnetic components to it, and this interacts with the magnetic component of the nucleus itself. Now let's consider what would happen. It would drop. And the interesting thing is the extent of where it would drop. It could drop from here to here, or to here, or even up to 90 degrees. It can actually flip up to 90 degrees and even get to here and spin flat. That's the maximum. And the extent to which it would drop, and the type of resonance we will see, the type of spin we will see, depends on its environment. So let's just say it dropped nearly to 90 degrees, and now this is its resonance. This is its resonance now. And it's slowly, being that now the radio frequency pulse has stopped, now it is going to go back and slowly align with the big spin lattice homogeneous magnetic field vector. So it's essentially going to spin around like so, spin, and come back. And as it's doing that, and this is the spin state, or you can call it the spin decay. Spin decay. Why is it decay? Because this vector that was created by the drop is slowly going back and is lost, you can say, because we're only getting back that one vector that we had. So again, we excited it with a radio frequency and it dropped. And now it's going to go back, and because we stopped with the radio frequency, it was only a pulse, and it's slowly going to go back and align with the spin lattice. So this spin-spin vector is going to disappear slowly because it only got energy for a short amount of time by a pulse. So this little spin-spin is going to decay. It is going to disappear. And that is why it's called spin-spin decay in this fashion and emit some sort of energy. And we can collect that energy and read it. And because we know the strength of the magnetic field, the type of nucleus, we can get this energy and solve for the chemical environment. And that is how we can get information by reading the respective resonance. And resonance is just this little uh, this little trip it's going through, and it's going from this state of being hit by radio frequency to going back to the spin lattice. This whole thing is its frequency. And actually, while it's in the homogeneous spin lattice, it also has frequency, which is almost undetectable. It just rotates to a very small extent around this little, just like these guys, to a very small extent. Very good. So, recapping real quick, what do we mean? And this is called a 90-degree pulse because it obviously is applied 90 degrees to the homogeneous magnetic field, because we want to get this guy here to drop down. Perfect. So what happens? First of all, I'm going to just write it down just to have another way of having it here. First of all, we have the homogeneous magnetic field. So we have, I'm just going to write external magnetic field, external magnetic field. And then what happens, I'm using a 90-degree or RF pulse. You can think of it in any way you want. So let's just say 90 degree. 90 degree. And now what happens is I have my respective spin states, and this happens to all the nuclei at the same time, because I can apply this radio frequency pulse throughout the entire population. So all of these are going to slowly drop, and I'm going to have one that spins this way, and one that spins this way, and one that spins almost at 90 degree, and one that spins in a total flat 90 degree. So all of them are going to drop down and then slowly decay and go back to the original orientation and emit some sort of energy. So I apply the 90-degree radio frequency pulse, and then I have my spin, and by saying spin, I mean those little guys that are dropping. Instead of collectively adding to a big homogeneous magnetic field vector, they're slowly, each of them is dropping down to his own specific resonance. So we have spin, you can say formation. I wouldn't say formation, but we say spin resonance. Spin resonance after the 90-degree pulse. And then after that, you have the spin decay. Spin decay. And why do we have the spin decay? We have the spin decay because we only use radio frequency pulse for a short amount of time, but the homogeneous magnetic field stayed on the entire time. So it's only a matter of time before they are going to go back to aligning using it. So it's spin decay, and this is also referred to as spin lattice. And the spin lattice is this thing, obviously, spin lattice or longitudinal, you can call it whatever you want. The spin lattice recovery. Let's switch colors here. Spin lattice recovery. This is the same thing. And then I can go back. Step 5 would be repeat step 1. And then I can get multiple readings about the specimen. And what's important to understand is we get the information. Let's just say this is the spin lattice, and when I applied a radio frequency, all the different spins dropped. And I'm going to take one here. Let's just say there's one here and one here. This is its resonance. This is its resonance. This dropped by a whole lot. This is its resonance. And these guys are going to slowly relax back into, or decay back into the big homogeneous magnetic field vector. And for this guy, it's going to look like this. This guy is going to take a longer time. It's going to go through more spirals. And this guy hardly dropped. It went like this. And when these guys emit energy, this would emit a certain energy, this would emit a different energy, this would emit a different energy. I can read this energy and gain information as to what the environment is, and why. Why does the environment affect this resonance? Well, think of it this way. Let's just say I have a spinning nucleus here. Let's just say I have water molecules. I have a water molecule here, and I'm checking the spin state on this hydrogen, and we know that this hydrogen has a covalent bond with a very electronegative ingredient here, and this electronegative ingredient, the oxygen, is going to affect the way this hydrogen is going to behave. Both it is going to behave once the effect of this homogeneous magnetic field is reduced for a momentarily amount of time by this radio frequency pulse. And this is basically chemical shift. Chemical shift, and this is important to understand, chemical shift is the way the chemical environment of the spinning nucleus, this is the spinning nucleus, let's not worry about this guy yet, but it's the way the chemical environment, and there could be other molecules around it, but it's the way the chemical environment changes or affects the resonance, or the way this would seem as it is spinning. This is what we call resonance, this spin, how the chemical environment would affect the resonance of this specific nuclei. So let's go through the minimals here. There we go. What kind of factors influence the resonance frequency in NMR? First of all, we already spoke about the quality of the absorbing nucleus, which is the type of the nucleus, its chemical environment, and the strength of the magnetic field. Being that we know what nucleus we're dealing with, what magnetic field we're dealing with, we can solve for the chemical environment and obtain information about the composition of my sample. Now, what is chemical shift in NMR? And this is quite important to understand. The local magnetic field, and by local magnetic field, I mean the magnetic field for this little dude here, for each nuclei. So the local magnetic field around a given nucleus is altered by the chemical environment, resulting in a change in its original resonance frequency. And being that I can collect all the energy that these guys emit, I basically can solve, and this is done multiple times in a sample and in an observation, but I can solve for what is around them. And I can get an information about what is in my sample. Okay, that was quite the video. Hopefully you have found this helpful, and you may need to repeat this video or at least rewind it to make sense of it all. Basically, what we've done here is we repeated and went through the relationship between the energy between the two spin states and the magnetic field. And just so you know, being that I mentioned it, if I have this much energy, it will relate to a specific radio frequency pulse, or this would also pertain to a specific radio frequency pulse, because I set what energy level this is by setting what Tesla magnetic field strength I'm using. And we also went to how we add up these different spin states into an integral longitudinal spin lattice T1. Wow, this is an N. Is this my handwriting? Holy hell. This is horrible. And also we went through what is the 90-degree pulse, or the RF pulse, that we use its magnetic component to impart some energy to the different little spin of the individual nuclei and make him drop away from the homogeneous magnetic field vector. And that way they can relax back to it and emit energy that pertains to what sort of chemical environment they have around them, and that is also chemical shift. In the next video, I'm going to hope to tie up all the loose ends and show you how chemical shift may look in the NMR spectrum. And I'll see you in the next video.